Welcome to another episode of AI 10X, brought to you by 10 Leaves.
Glad to be here.
And welcome to you, the listener.
Yeah.
It is really great to have you joining us for this session.
It really is.
Because whether you are, prepping for a strategic meeting on autonomous tech, or trying to catch up on the latest paradigm shifts in the aerospace sector, or if you're just simply curious about the operational logistics happening way out there beyond our atmosphere, you are absolutely in the right place.
Definitely. We've crafted this deep dive to be a custom-tailored journey just for you.
Exactly. And it's a topic that, honestly, it feels like it belongs in a speculative fiction novel, but it is rapidly becoming the foundational reality of modern aerospace engineering.
It is a profound shift. I mean, today we're looking at how the edge of technological innovation is moving right into the void of space.
Yeah.
And we're going to explore this at a pace that respects your time, focusing on the real architectural changes and how we approach interplanetary logistics.
Right, rather than getting bogged down in those basic introductory concepts that, you're likely already familiar with.
Exactly.
So today's source material, we are pulling from some incredible excerpts from a document titled AI 10X: The Autonomy of Off-Earth Exploration.
A fantastic text.
It really is. So, okay, let's unpack this.
Let's do it.
The mission for today's deep dive is to understand the mechanics of how artificial intelligence is moving beyond Earth to power off-planet exploration.
Specifically focusing on two highly complex applications.
Right, the deployment of autonomous rovers
And the emerging concept of off-Earth mining.
Yeah, off-Earth mining. We need to explore why these technologies are an absolute necessity, how they actually function in such a hostile environment, and really what they mean for the future of humanity's footprint in the cosmos.
The most logical place to start here is with the fundamental bottleneck, the bottleneck that space exploration has just always faced.
Right.
It's the primary catalyst driving all of the specific AI development, and that is the insurmountable problem of distance.
The distance problem. It is fascinating because it fundamentally breaks our traditional understanding of control.
It shatters it entirely.
We are dealing with environments where communication delays make real-time human control physically impossible.
The laws of physics just don't allow it.
No, they don't. I want you, the listener, to really think about this for a second. Think about the latency issues we deal with in high-frequency trading.
Or cloud computing right here on Earth.
Right, where a delay of mere milliseconds can cost millions of dollars and just ruin a perfectly good algorithm.
Now scale that latency up.
Exactly. Scale it up to 14 or 20 minutes.
It's staggering.
I mean, imagine playing a remote-controlled game, right? You've got the controller in your hands, but your vehicle is millions of miles from Earth.
You push the joystick forward.
And nothing happens. Not for 20 minutes. You aren't just dealing with lag at that point. You are dealing with a fundamental break in causality between the command and the action.
That break in causality, that's the perfect way to frame it. The sheer scale of interplanetary distance changes the entire architecture of an operation.
Because of the speed of light.
Exactly. Information, radio signals, telemetry, they are all bound by the speed of light.
Right.
When a machine is operating deep in the solar system, that travel time becomes a critical, persistent operational hazard. You simply cannot have a human being holding a joystick in a control room in Houston or Pasadena.
Because if something goes wrong.
Right. If the environment suddenly changes or if a structural hazard appears, the human operator on Earth is literally looking into the past.
Looking at a video feed of a disaster that already happened 20 minutes ago.
Exactly.
But let me push back on that for just a second, because we have been sending probes and landers to other planets for decades using that exact model.
We have.
We send a command, we wait for the ping, we analyze the telemetry, and then we send the next command.
Right, the step-by-step approach.
Yeah. So why is that methodical, step-by-step process suddenly obsolete?
It becomes obsolete the moment you transition from a static lander to a dynamic, moving vehicle operating in unpredictable terrain.
Okay. The movement changes everything.
It changes everything. If you're relying on that step-by-step process for a rover, the mission slows to an agonizing crawl.
You'd move inches a day.
If that. You are wasting the operational lifespan of a multi-billion-dollar asset waiting for a signal to bounce back and forth across the solar system.
Just burning through time and money.
Furthermore, if a rover is in motion and encounters a sudden threat, say, a collapsing sandbank, a 14-minute delay means the vehicle is completely destroyed before the first warning light even flashes on a monitor on Earth.
Wow.
The technology must be self-reliant because the laws of physics afford us no other option.
Which naturally brings us to the solution provided in the text.
Yeah.
AI-enabled autonomous rovers.
The only viable path forward.
We are moving away from machines that just execute a pre-programmed sequence of driving commands.
Right.
These newer systems, they're defined by two vital capabilities.
Yeah.
Real-time navigation and adaptive decision-making.
Now, what's fascinating here is how we define adaptive.
Break that down for us.
We need to really look at what that practically requires of a computational system operating millions of miles from home.
Yeah?
Real-time navigation implies that the rover is continuously mapping its environment. It's using a suite of sensors to render a three-dimensional understanding of the terrain immediately in its path.
So it sees the rocks, the dips, the hills.
Exactly. But the adaptive decision-making, that is where the true engineering leap occurs. It elevates the machine from a simple automaton to a dynamic priority engine.
A dynamic priority engine, I like that phrase. But how does that actually work in practice, though?
It's highly complex.
Because adaptive sounds great in a controlled laboratory setting. But if an AI decides to override its pre-programmed route and reroute around an obstacle, isn't there a massive risk it drives into a softer terrain trap or maybe a steeper incline?
There is always a risk.
So how does a machine weigh that kind of existential risk without a human gut check?
That is the multi-billion-dollar question. To do this, the AI must possess an incredibly robust internal modeling system.
Internal modeling.
Right. It isn't just reacting, it is predicting.
Okay, give us an example.
Imagine the rover is given a broad, high-level directive from Earth. Something like, navigate to the base of that ridge and begin geological sampling.
Simple enough.
Right. So the rover begins its journey. Along the way, its sensors detect an unexpected crevasse blocking the most direct, pre-calculated path.
A physical roadblock.
Exactly. Now, an adaptive system does not shut down and enter safe mode to wait for Earth's permission to detour.
Because waiting burns mission time.
Correct. Instead, the AI analyzes the crevasse, calculates a dozen alternative routes, and then simulates the outcomes of those routes locally.
It plays out the scenarios in its own head, basically.
It assesses the structural integrity of the surrounding terrain, factors in its current battery levels, calculates the solar angle for recharging on the new path.
The solar angle. It's thinking about where the sun will be.
It has to. And then it decides in a fraction of a second on the safest and most efficient detour. It is performing a highly complex risk assessment matrix entirely on its own.
So it is essentially functioning as its own mission control.
That's a great way to put it.
It is taking the overarching strategic goal provided by human scientists and independently figuring out the tactical execution.
Yes.
It evaluates threats, simulates futures, and commits to a course of action.
It has to function that way. The AI allows the mission to proceed at the speed of the immediate environment rather than the speed of interplanetary communication.
The speed of the environment.
Right. The rover becomes an active participant in its own survival and success. It's constantly balancing the primary directive of the mission against its own self-preservation parameters.
That is just a staggering level of autonomy for a machine.
Truly unprecedented.
And yet, when we look at the broader trajectory of space exploration in this document, merely driving around and analyzing terrain is just the beginning.
It's just phase one.
Here's where it gets really interesting. We are seeing a distinct pivot from exploration to actual resource gathering.
Yes.
This is where the concept of off-Earth mining comes into play.
We are witnessing the theoretical foundation of an extraction economy moving into the solar system.
An extraction economy in space. We are talking about deploying artificial intelligence to target asteroids.
Asteroids, yes.
We are looking at a future where we utilize these autonomous systems to mine valuable, rare materials from spaceborne bodies.
And to accomplish this, the AI's role expands significantly.
Right. The text breaks it down into two distinct, highly complex functions.
Identifying the resources and extracting them.
Those two functions.
Gainer.
They represent a massive escalation in computational complexity.
Huge escalation.
Let's dig into that first function, identifying the rare materials on an asteroid. Again, we have to completely discard the idea of a human scientist looking through a high-resolution camera feed and pointing out a promising vein of ore.
The delay makes that impossible.
Exactly. The AI has to conduct the identification autonomously. But a tumbling asteroid is a chaotic environment.
Extremely chaotic.
How does a machine definitively judge a chemical signature without human oversight?
It requires the AI to function as an autonomous prospector,
A robotic prospect.
equipped with an array of complex sensors. We're talking spectrometers, ground-penetrating radar, chemical analyzers.
Okay.
As the spacecraft approaches the asteroid, it has to process immense streams of raw data.
While matching the rotation and speed of the rock.
Yes, and it must compare that incoming sensory data against massive internal libraries of geological models.
Because it can't query a database on Earth.
Exactly. It has to understand what specific rare materials look like on a molecular level under various lighting and radiation conditions.
So it is cross-referencing real-time sensory input with a deeply embedded geological database, millions of miles away from a human lab.
And it must make a definitive judgment call based on that cross-reference.
No second guess.
It has to conclude, this specific coordinate on this moving body contains the target element at a density worth extracting.
Wow.
It is performing advanced data analysis, geology, and chemistry simultaneously in the void of space.
Which is an incredible feat of software engineering on its own.
Absolutely.
But once it finds that optimal location, it has to move to the second function, which I would argue is infinitely more dangerous.
Extraction.
Extraction. Extracting those rare materials. This isn't passive observation anymore. This is kinetic, physical interaction with a celestial body.
Extraction is where the stakes reach their absolute peak.
Yeah.
This involves deploying drills, lasers, or capturing mechanisms.
And doing it perfectly.
The AI has to calculate the unique physical properties of the asteroid, its microgravity environment, its density, its rotational spin, and it has to adjust its extraction tools accordingly in real time.
That kinetic feedback loop must be intensely complicated.
Yeah.
I mean, think about drilling into rock here on Earth. The human operator feels the vibration. They hear the pitch of the motor change, and they intuitively adjust the pressure so the drill bit doesn't bind or snap.
It's a tactile process.
Exactly. Now, put that operation in a zero-gravity environment, where pushing a drill into a rock pushes the spacecraft equally hard in the opposite direction.
That is the exact engineering hurdle. If the drill hits a harder layer of composite material than the initial scans predicted, the AI must instantly adapt its downward pressure and rotational speed.
In a fraction of a second.
If it doesn't, it could break the equipment. Or worse, completely destabilize the spacecraft's orbit around the asteroid.
A total mission failure.
It is managing a highly delicate physical-industrial process in one of the most hostile and unforgiving environments imaginable.
And what absolutely solidifies the necessity of this technology, what the text really drives home, is the explicit requirement that all of this happens with minimal human control.
Minimal human control.
The targeting of the asteroids, the complex spectrometric identification of rare materials, the physical kinetic extraction. It all occurs with the human operators largely removed from the loop.
Minimal human control is the phrase that ties this entire technological leap together.
It really is the anchor point.
It connects right back to our initial discussion regarding the latency of communication.
Right, the distance problem.
You cannot remotely operate heavy mining machinery on a tumbling asteroid from a desk on Earth. The time delay would cause you to shatter the drill bit or crash the spacecraft before you even saw the telemetry indicating a problem.
You'd just get a screen full of static 20 minutes later.
Exactly. The AI must be in absolute control of the minute-by-minute, millisecond-by-millisecond physical operations.
If the AI is handling the tactical execution, the navigation, the risk assessment, the identification, and the physical extraction, what exactly does minimal human control look like?
That's a good question.
Does our role simply become administrative?
We essentially transition into the role of strategic managers.
Strategic managers. Okay.
We provide the intent and the overarching parameters. We dictate the mission requirements. We say, we need this specific volume of this specific element by this specific date.
And then we let go of the steering wheel.
The AI handles the logistics required to fulfill that intent. Human engineers might monitor the high-level progress and review the post-action telemetry, but the real-time execution is entirely delegated to the machine.
It requires a profound level of trust to delegate that much responsibility to an autonomous system.
An immense amount of trust.
We are talking about fleets of advanced spacecraft operating out in the deep black, maneuvering around asteroids, evaluating their composition, mining them, and securing resources, while we sit back here on Earth entirely hands-off.
It represents a fundamental shift in humanity's relationship with our own creations.
It does.
We are no longer just building tools that extend our physical reach. We are building independent agents capable of carrying out complex multi-stage industrial missions in environments where biological life simply cannot function.
So what does this all mean for you, the listener? Let's connect the massive scale of interplanetary AI back to your own understanding of where technology is heading.
The big picture.
Exactly. The concepts we've explored today, autonomy born out of the strict limitations of physics, adaptive decision-making, prioritizing dynamic risk assessment over pre-programmed scripts, and the delegation of complex physical tasks to machines with minimal oversight.
These are the architectural pillars of the next generation of exploration.
In space, these aren't just fascinating engineering trends, they are the absolute prerequisites for progress.
They are the ultimate bottleneck. Without these advanced AI capabilities, our exploration of the broader solar system remains severely limited by the speed of light and the fragility of human biology.
We'd be stuck.
By solving the autonomy problem, the solar system essentially opens up to industrial and scientific expansion.
Which brings us perfectly to the core thesis of this entire paradigm shift as laid out in the source material.
The role of AI.
Right. The role of artificial intelligence is fundamentally changing. It is no longer categorized merely as a sophisticated tool. It is evolving into humanity's co-pilot in space.
Co-pilot is a deeply intentional and accurate term here.
Because it implies partnership.
Exactly. A tool is a static object. It is something you directly manipulate to achieve a singular result. You hold a hammer, you swing it.
Right.
A co-pilot, however, is an entity you trust with the safety of the mission. It is an agent that shares the burden of the journey, that makes independent, critical decisions when the primary pilot, in this case, humanity on Earth, is too restricted by distance to react in time.
It is a partnership defined by sheer necessity. We are trusting the AI to sit in the seat next to us, figuratively speaking, and take full control of the execution because the vast cosmic distances demand it.
We have no other choice.
We have covered significant conceptual ground today, moving from the physics of communication latency to the incredible operational realities of autonomous asteroid mining. But before we wrap up this deep dive, we want to leave you with a larger philosophical implication to consider.
This operational shift raises an important question, something I highly encourage you to mull over as you analyze the future of aerospace technology on your own.
Let's hear it.
We have established that the laws of physics and communication delays force us to rely entirely on AI for real-time navigation.
Right.
We must rely on it for adaptive, life-or-death decision-making. We must rely on it to autonomously identify and physically extract resources from celestial bodies with minimal human control.
The machine does the heavy lifting.
Exactly. If all of these deeply complex, critical, and defining tasks of exploration must be handed over to an artificial intelligence.
Or rather, because they must be handed over.
Yes, because they must be. At what point does space exploration stop being a strictly human endeavor and become an entirely AI-driven frontier?
That is a brilliant and heavy thought to end on. If the machines are the ones actively making the decisions, assessing the risks, finding the rare materials, and navigating the void, whose exploration is it really?
Exactly.
That is a question the aerospace industry and society at large will be grappling with for decades to come. Thank you for joining us for this in-depth analysis. We hope you walk away with a sharper, more nuanced understanding of the autonomous logistics reshaping our approach to the cosmos. Keep analyzing, keep questioning, and keep exploring. This was AI 10X presented by 10 Leaves. Welcome to another episode of AI 10X brought to you by 10 Leaves.